Okay, so continuity and limits analytically. So what does it mean for a function to be continuous? So for continuity, a function is continuous at a point x equals a if the following is true. 1, the limit as x approaches a from the left-hand side of f of x equals the limit as x approaches a from the right-hand side of f of x. And I do want to point out that this means that we have the limit as x approaches a of f of x. And 2, the limit as x approaches a of f of x equals f of a. So if these two statements are in fact true, then the function is continuous at x equals a. Now, what does that mean for us graphically? Graphically, in layman's terms, is that you do not need to lift your pencil when going through x equals a. If I drew a graph, and let's say this is 1 and this is 3, this graph does this here, and then right over here, let me redraw this graph because I got a little bit. And the graph does this. Well, what is f continuous? This is the graph of y equals f of x. Sorry about that. This is the graph of y equals f of x. And we don't always use y equals f of x. Sometimes it's y equals it's y equals g of x and so forth. But is f continuous at x equals 1? In this example right here. Yes or no? So, I just realized my sound is going down. So what is that?
I did so when I do just to it, take a vertical is connected with the x equal something number. Let's see what number is connected with number.
Well, the question here is there's no vertical lines, first off. So the question here is at x equals 1, at this value x equals 1, is the function continuous? Well, first off, if we look at the limit from the left-hand side, and we look at the limit from the right-hand side, they're both pointing to the same coordinate. Yep. And it has the same point right here. So I didn't put any output actually value. So in this case, though, f of x is continuous at x equals 1. And the reasoning why, of course, is because the limit as x approaches 1 from the left of f of x equals the limit. Let me actually rewrite this a little bit over to the side. The limit as x approaches 1 from the left-hand side of f of x equals the limit as x approaches 1 from the right-hand side of f of x, which is equal to the value of f of 1. However, if we talk about x equals 3 right here, f of x, is f of x continuous at x equals 3? The answer is no. Good. Is not continuous at x equals 3. And the reasoning behind here is that f of 3 is undefined. So there is no value at f of 3. And while the limit at x approaches 3 of f of x exists, it does not equal f of 3 because there is no value for f of 3. So visually, these are what limits with continuity and continuous functions work. And this idea behind so there's always a big mix-up amongst students when they're working on this material. A lot of students will confuse, does the limit exist versus is the function continuous? And just because a function exists doesn't mean that the limit, or sorry, just because a limit exists doesn't mean the function is continuously. A lot of this times it's a lot easier for us to see this visually than it is for us to do it analytically. Now, the converse is true, and this right here has a very strong implication from us. And it says that, okay, so if these facts were true, then the function was continuous. If f of x is continuous, okay, the converse, the opposite, then the opposite must be true. And then that means then the limit as x approaches a of f of x must equal f of a. And this small property here is a very important property that allows us to evaluate limits. So it's a very important property here that if this is true, we are able to do it. And I kind of realized I opened up the meeting, and these notes are going to keep having people pop in because a lot of people are coming in late or having internet issues, and I'm having to do it over here of letting people in. I just realized that, but there's nothing I can really do. So when you're watching the screen, you might see people's names pop in when they were trying to join. So I just want to give you a heads up on that. So if a function is continuous, then if a function is continuous at a point, of course, then the limit at that point, so I'm going to put this up here, at x equals a, then this is true. And I also want to note that if a function is continuous everywhere, then the function is continuous at x equals a. And that's kind of like, so if I told you that this function is continuous everywhere, then of course, is it continuous at x equals 2? Yeah, because it's continuous everywhere. This has a lot to do with something that's like domain. So I want to point out a couple of functions. One, polynomials are continuous and this is what we refer to as interval notation from negative infinity to infinity. Everywhere. All right, so that notation means, and these are the x values. When I utilize this notation, these values mean for all x values. Sometimes you might note that we sometimes use the notation with an R with an extra line through it. In AP Calculus, we utilize interval notation more than anything else. So polynomials, if you're dealing with a polynomial, there is no denominator. X is not in denominator. It's always like x to the 5th power plus x7, x to the 12th power, and so forth. Those functions are continuous everywhere. 2. Exponentials are continuous from negative infinity to infinity. So an exponential function is continuous everywhere. Now, why are these statements true? If you're wondering why are they continuous everywhere? These have to do with the graphs. So in pre-calculus or in Math 3 or during the summer program that you took with me in Bridge to Calculus, you should have had a strong understanding and learning of what the graphs look like for polynomials. If you draw a polynomial, you will never have to lift up your pencil. If you draw an exponential function, you never have to lift up your pencil. So polynomials look, like that. Exponentials look like this, or they look like that. Those functions, you'll never have to lift up your pencil when drawing. Finally, 3, sinusoids are continuous from negative infinity to infinity, everywhere. Sine of x, cosine of x, those are continuous everywhere. Well, not all functions are continuous everywhere. We also have some other functions to understand. Radicals. For example, y equals the square root of f of x is continuous when f of x is greater than or equal to 0. Logs, such as y equals the log of f of x, is continuous when f of x is greater than 0. And these have to do with just domains, right? You can't take a radical of a negative value. You can't take the square root of a negative number. Logs, you can't take the log of a negative number. Or 0, you can't take the log of 0. The log of 0 is undefined. And 6, rational functions, y equals 1 over f of x, is continuous everywhere except f of x does not equal 0. So as long as the denominator, because if f of x equals 0, you would get 1 over 0. 1 over 0 is undefined. Okay. So the basis and the premise of what we are talking about here. Sorry, I couldn't hear you, Darwin. Did you have a question?
No, I have a question. I only read it.
Okay, you put your mic back on, that's why. So when you put your mic on, that tells me that you're asking a question. So just continuity is a very important piece. Evaluating limits. So the main premise here is that in order for us to do things in calculus, you need to understand why you're able to do that. You can't just do things magically. For example, you can't just I'm not, like, how are you able to do that? Why are you able just to plug in is going to be the answer. And it's because of continuity, not just because your teacher told you that that's how you do something. So, evaluating limits. So, as we just said, if f of x, and just repeating it, is continuous then the limit as x approaches a of f of x equals f of a. Let's look at a quick example. It's easier than you would think. Calculus, and I will repeat this throughout the year, calculus is not very hard to do for the majority of problems. The actual concepts of calculus are really not hard. What I'm going to be teaching you that's new really isn't much harder. I think pre-calculus math 3 is a lot harder in terms of the techniques, the concepts that we are doing. If you mastered those topics, you should be able to master these ones. But here's the problem. Most students don't master the previous topics. And the hard thing about calculus is that if you have any struggles algebraically, if you have any struggles with your pre-calculus function analysis, then calculus is hard because calculus requires it. The number one thing about calculus is that calculus requires you to do everything that you've really done in your previous math courses. So if you forgot how to solve an equation, if you forgot how to do a quadratic factoring, if you forgot how the graph of an exponential function looks like, if you forgot how to multiply numbers, those are the problems that make it struggle. And more importantly, in calculus, more than any other class, if you miss a lesson, well, you can't really oftentimes do the next lesson because every lesson in calculus basically builds upon itself. If you don't have a strong understanding of limits, you're not going to understand why you're able to or how to do the next problems. If you don't know how to do the problems for one day, you can't do the problems for the next day. So if you are not at your screen taking your notes, if you're not asking questions, if you're not doing your homework on a daily basis, in calculus especially more than any other course, you won't be able to do tomorrow's lesson. And then if you can't do tomorrow's lesson, you can't do the next day's lesson. And all of a sudden, you're like 3-4 days behind and you can't do anything because you missed one lesson. And that's the biggest issue here. So here's the example. Evaluate. A. What is the limit as x approaches -3 of x squared? So that's the question. This is a basic limit type of problem. Well, when I look at this function right here, y equals x squared is a polynomial. This is what I'm thinking of in the back of my head real quickly. And sometimes it's x squared. It's a polynomial, so which means it's continuous. And because this is continuous, you don't have to write that information that I just wrote down on the bottom, but x squared is a continuous function. So is x squared continuous at x equals -3? Yes or no? Is y equals x3 or y equals x squared continuous at x equals -3? Yes or no?
I think so. Yes.
It's continuous. So the answer is yes. It's continuous everywhere, so it's continuous at x equals -3. So all I have to do, it's as simple as this. -3 squared. You're just plugging in. So it's -3 squared. But make sure, of course, you got to know how to evaluate these. Biggest mistake students get is they say that it's -9, but no, it's -3 quantity squared, which gives me 9. And that's the answer. Boom, that's it. Now, other properties before we get into the other examples. And most of these are obvious. So properties. The first one is called the sum and difference property. It says that the limit as x approaches a of f of x plus or minus g of x. So if I add two functions, and it's basically it's exactly as what you think it is. And what I mean by that is that it's just equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. Now, some of you are going to say, well, can I just plug in then? Can I just plug in x equals a for f and g, and there's my answer? And the answer is yes. If you're doing this problem analytically, in other words, I give you an actual functions, one's maybe an exponential function, one's maybe a polynomial function, all you do is plug in. However, sometimes I give you the problems graphically, like in the previous class. Sometimes, and as what will happen is you'll get a problem that is, oh, f is this function. I'll give you the equation for f, but I'll give you a graph for g. Okay? Now, something that should be noted here, I just want to point out that if f, sorry, and I'm not going to write this all the time, but if the limit as x approaches a of f of x, or the limit as x approaches a of g of x does not exist, then the sum slash difference does not exist. So if either one of these limits is a does not exist, then the answer for the entire problem is does not exist. Okay? Multiplication. You did this one, you technically did this one in your homework. And for those of you who haven't completed your homework, I have slowed, and I see comments, I have slowed this course down for the beginning as much as physically possible. I have slowed it down. I have taken single lectures and combined them to two. I waited, 4 days before we even got to our first lessons. I've made the homework problems, online in terms of clicking. So I have slowed down the process entirely as much as I can, with the main premise that, hey, you're learning where to go to do problems. And if you don't do the problems, then there's nothing that I can do to slow the course or direct you in any other way. You still have to, it's an AP course. And what that means is you have to take the responsibility that every day you're going to complete the homework. If you can't make a lesson, it's still posted online. The notes are still posted online. The homework is still posted online. So you can't give yourself an excuse not to do it, no matter if you're able to make the Zoom session or not. And you're going to learn best by being here with me, but it's not the only way to learn. The multiplication rule of limits is that the limit as x approaches a of the product of a function, f of x times g of x, is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. And this was in one of your Delta Math homework problems on the second set. And it basically says that, okay, if you have a limit of two functions, and once again, I can give you each of these functions as their own graph or their own equation. So I can say, here's the graph for f, here's the graph for g. You're going to do each of them as two separate problems. Now, of course, the same thing is true on top that I wrote down below. If the limit does not exist, for either of these, let me capture this a little bit better. There we go. If the limit does not exist for either of them, then it does not exist for the multiplication of them. I mean, it seems kind of obvious. The same things keep coming up over and over and over. Now, in the problem for Delta Math, you got two graphs. So you find the limit for f at that point. You find the limit for g at that point. And if both values do exist, then you multiply your answer. Quotient. I think you should be understanding it's a pattern. There's a lot of patterns in calculus. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. If the limit as x approaches a, or sorry, okay. If the limit as x approaches a of g of x does not equal 0, or of course does not exist. So if the denominator is 0, there's some special circumstances that we will get into and we will learn about it, but the denominator can equal 0. If you get a constant divided by 0, okay, then the answer is does not exist. If you get 0 over a constant, then mathematically 0 divided by anything that's not 0 is 0. And if you get 0 over 0, this is in tomorrow's lesson. So we'll talk about what happens when you get 0 over 0. But 0 constant divided by 0 does not exist. And when I say does not exist for those type of problems right there, really this is the idea of a vertical asymptote. So when you divide by 0, that's if you go back to your pre-calculus math 3 understanding or the summer bridge to calculus, when you divide by 0, when you evaluate what's referred to as a rational function, that's how you get a vertical asymptote. And finally, the composite, which was the one I was trying when I emailed you. And I don't send very many emails through the stream, so when I do, it is best for you to make sure that you do check them. For the composite, it says that we have the limit as x approaches a of f of g of x, okay, is equal to f of the limit as x approaches a of g of x. If f of x is continuous at g of a. So this was the tough part right now, because when I was saying my message to you, I hadn't yet really said the word continuity. I hadn't really said the word continuous. But the function itself must be continuous at that value. So for example, on this last one, this one's a really big one. And I'm going to do this problem analytically versus graphically like you did on your homework. F of x is equal to 3x squared. G of x is equal to 5x. Find the limit as x approaches 2 of f of g of x. Okay, so that's the question. Well, based on the property we learned now, of course, you can actually utilize pre-calculus math 3 skills to actually take the composite and put 5x into 3x. So you get 5 times the quantity 3 times the quantity 5x squared. You could do that. You could do it that way. But the idea here is what happens if you're given the problem graphically. So this is equal to f of the limit as x approaches 2 of g of x, which is equal to the limit, which is equal to f of the limit as x approaches 2 of what g of x is 5x. And I'm doing way more steps than you'd probably do in real practice. F of 5 times 2, which is f of 10. Okay, well, what is f of 10? F of 10 is 3 times 10 squared, which is 300. Now, there is a secondary part on this question. You have to got to make sure f of x is continuous at x equals 10. And how do I know that the function is continuous at x equals 10? How do I know that f is continuous at x equals 10? It comes from something that I mentioned earlier in the lesson. Look at f. Why is that function continuous at x equals 10? It's a polynomial. Yeah, perfect. F of x equals 3x squared is a polynomial function. I showed you and talked to you about the graphs of piecewise functions. So now let's finish and talk about the last part of today's lesson, which is evaluating limits of piecewise analytically. Okay, so we're talking about piecewise functions. In the previous lecture, in terms of review, I gave you a graph that might have looked like the following. It might have looked like this. And then you had the graph here, and you had right here. And this was, let's say, this was the value x equals 2. Okay. Graphically, I can ask you about the limit as x approaches 2 from the left-hand side of f of x. And we would start from the left of 2, somewhere like over here, and go approach the value. And then I would ask you about the limit as x approaches 2 from the right-hand side of f of x, which means we would start to the right over here, and we would get closer to 2. And I would evaluate this problem. Well, you can see that these two values do not equal each other. Therefore, the limit as x approaches 2 of f of x does not exist. Or we could also say that f of x is not continuous at x equals 2. Because, remember, for a function to be continuous, the limit has to exist. If the limit doesn't exist, then automatically the function is not continuous. However, that's how we would read it graphically. And so first off, and this is a perfect example of prior lesson requirements. If you don't know what I mean by left-hand limit and right-hand limits graphically, then it is near impossible for right now in the instance to be able to understand how left-hand limit and right-hand limit work analytically. And I gave you 2 days, I gave you multiple days of homework and time to ask questions and time to master it, to even ask a question about graphically. And you can't just put it aside. You can't just not do it. You can't just not say, oh, I don't understand. I'm going to move on to the next topic, because it requires it in calculus. So let's do an example. And it's actually the example of this function on top. So how are we writing these problems? We write them as f of x equals, and hopefully, you've seen a piecewise function before. If you haven't seen a piecewise function, then we're going to have to work on understanding those a little bit more outside. I can give you some Khan Academy. I can get you some Delta Math review on piecewise. It's no problem. I can just give you those as extra problems on how to evaluate piecewise. And we go with 3 minus x for x less than 2. Now, what this means is that for all x values less than 2, the function of x will look like the line 3 minus x. If you look on that top problem, that's basically what I'm referring to. For the values less than 2, for the x values, the graph looks like 3 minus x. 3 minus x is a line, and it would intersect with a negative slope, intersecting the y-axis at x equals 3. And it acts as the function x minus 3 squared plus 2 for when x is greater than or equal to 2. X minus 3 squared plus 2 is a quadratic written in vertex form, with the vertex being located at 3, 2. All right, so I mean, these are the type of things. Now, of course, you really don't need to know that specific part to be able to do this problem, but making sure you understand what we're dealing with. Both of them are continuous functions, so you're able to answer the question. So here's the first question, A. What is the limit as x approaches 2 from the left-hand side of f of x? All right, so left-hand side of 2, is that less than 2 or greater than 2? 2 from the left-hand side. Is that dealing with values of 2 that are less than 2 for x or greater than 2 for x? Less than. Yeah, it's less than. So that means that this is equal to the limit as x approaches 2 from the left-hand side of 3 minus x. I know this because this function acts like x less than 3 minus x for when x is less than 2. Now, a lot of students will go, wait a minute, how do I evaluate one-sided limits? Well, you evaluate a one-sided limit just like you do a two-sided limit. Because, and this is a little bit more, maybe more than you really need to know, but I think it's important. If the function is continuous, then the two-sided limit equals the function value, which therefore means that the two-sided limit exists. There's a value for the two-sided limit. And the only way for a two-sided limit to exist is if the left-hand limit and the right-hand limit not only exist, but they equal each other. So, long story short, all you need to do is plug in the value. 2. Which gives me 1. B. What is the limit as x approaches 2 from the right-hand side of f of x? Well, this is the same thing as the limit as x approaches 2 from the right-hand side of, and I wrote, and actually I'm not gonna write the right-hand side on this time because I know which function I have to utilize. I have to utilize this x minus 3 squared plus 2. I want to note that in here, I didn't write the plus, but it works the same. You just need to identify which function you are using. So all I got to do now is plug in 2. 2 minus 3 squared plus 2. That's negative 1 squared plus 2, which is 1 plus 2, which is 3. Now, in my assignments, in my problems, in your quiz, on the AP exam, you may be asked to find the left-hand limit and then the right-hand limit. But sometimes you are only asked, what is the limit as x approaches 2 of f of x? And this is the only question. Well, to answer this question, question C, you have to, on your own, recognize that you have to first find the left and the right-hand limits. Well, what is this answer? Perfect. Does not exist. Now, if I say justify, explain your reasoning. You can't just say D&E and expect full credit if I ask you to explain your reasoning. If this was the only piece, in other words, if this was the only question that you saw, you didn't see the question on top, and you just wrote D&E, your answer is right, but you won't receive full credit. at best, you'll receive half credit. And the reason is because the limit as x approaches 2 from the left-hand side of f of x does not equal the limit as x approaches 2 from the right-hand side of f of x. If a problem ever states to explain your reasoning, you must show this, or you get, sometimes on the AP exam, no credit. D. Is f of x continuous at x equals 2? Is the function continuous at x equals 2? Explain. Yes or no? No. And the reason why is because the limit as x approaches 2 from the left-hand side of f of x, once again, does not equal the limit as x approaches 2 from the right-hand side of f of x. Remember, there's 2 rules for continuity. I wrote them up top. Right at the beginning of the lecture. The left-hand side has to equal the right-hand side, so you need a check mark there. And the limit has to equal the function value. So it's 2 things. Whenever I ask you, is continuous, you have to go back to these definitions right here, and you must make sure that you're checking these 2 definitions every time for continuity. Seven minutes. We're doing perfect on time. Let me give you our last example. G of x, I'm going to switch it from f, is equal to 3x squared minus 6 for x equals 5. And 4x plus 2 for x not equal to 5. Now, this piecewise function notation is a little bit different than the less than or greater than symbols. You have to understand that this right here, especially this part, says everywhere except x equals 5, which means left side and right side. So you can think of this as saying x less than 5 and x greater than 5. It's both. So when you see the not equal to, it's actually referring to left and the right. The question I have for you is f of x continuous at x equals, well, what do you think I'm going to ask you? At x equals what? Is f of x continuous at x equals... We call this the critical point. And this problem is 5. And I'm going to do it and explain. So, before we do any actual evaluations, will the left-hand limit equal the right-hand limit? And the answer here is I don't need to actually even attempt the problem. But will the left-hand limit equal the right-hand limit? Yes or no? Or I don't know. Meaning I have to check. Yes, no, I have to check. Does the left equal the right?
I think it's not.
It actually does. Because it's right here.
Yeah, it's so more of the 5 is it's left on the 5.
Yeah. Because whenever you deal with the left-hand limit and the right-hand limit, they're always going to be true. So when you're dealing with not equal to, so when you see the not equal to symbol, automatically left-hand limit will equal the right-hand limit. It's going to happen because you're going to use the same function. You're going to use 4x plus 2. So whatever you get for the, how do you evaluate the left-hand limit for f of x, 4x plus 2? You plug in 5. How do you evaluate the right-hand limit for 4x plus 2? You plug in 5, or for g. You're going to plug in 5 for both of them. So automatically this one is true. I don't even have to check. So almost you have to ignore it. Or of course, you have to justify, so you still have to explain that. You know, it's going to be 4 times 5 plus 2, which is going to give you 22. So let's look at the second piece. What is the limit as x approaches 5 for g of x? Well, this is the same thing as the limit as x approaches 5 for 4x plus 2. A lot of people will think that you have to plug into the 3x squared minus 6, and that is not the case. You plug into the 4x plus 2 because that says everywhere away from 5, which means that those are what you use and what you would walk along to evaluate the limit, which is 22. Okay, well, what is g of 5? Well, to find g of 5, that means at that point, 5, I use the 3x squared minus 6. So this is 3 times 5x squared minus 6. You use that x equals 5 part of that. And that gives me 69 if I do the algebra right. It is. All right, so I got the limit as 22. I got the point value is 69. That means that if I were to look at this graph, the graph would look something like this and like this. Is this function continuous at x equals 5? No. Not continuous at x equals 5 because the limit as x approaches 5 of f of x does not equal f of 5. Nice, beautiful answer and work. It is 9:03. We have 2 minutes left in class. You have homework number 4, and it's going to come on Delta Math. I have already posted it to release. Have a great day. Hopefully I'll see some of you at office hours. You can't take those lightly. I am also going to, and for those of you who are like, I am struggling, we do have a tutoring service. I know it's still kind of remote and everything, but there are tutors available even outside of me. If you can't make it during those times or you need more time outside so that you can practice, there are tutors with a program called Pi R Squared. Some amazing calculus tutors that I want to make sure that I can connect you with. I'm going to be working there. They're really, as long as, I mean, to pay for a tutor, especially in calculus, a cheap tutor would be $50 an hour. All right, you can get $50 over $100 an hour for one-to-one tutoring. It's expensive. Pi R Squared offers it for free. The main thing here is that there's a couple of requirements. A, that you're gonna schedule a time for tutoring, and B, that you don't miss any tutorings. If this sounds like an individual such as yourself and you want to take advantage of this great opportunity, please come to office hours. I'll post more information as I can find it. If you come to office hours and specifically ask me, I'll make sure to put you at the front charge to get you those tutoring hours. With that, have a great rest of your day, everybody.